to go to degeneracy, right? Maybe here are the negative definite forms. What I am drawing here is an exact picture. These things are cones. Isn't that obvious? If I take a form and multiply it by 27, it has the same signature. It just changes the eigenvalues, right? So these are really cones. So you have the cone of positive definite forms. You have the cone of negative definite forms. You have the cone of signature 3, 1. You have signatures clearly an invariant here, right? So you have, and it's an open condition. Do you understand what I mean when I say it's an open condition? You take the point and you move it in an open set, it doesn't change. You agree that signature is something that does not change by small earthquakes, right? Small hurricanes, right? Up here in Bremen, sometimes the wind's really heavy, so you maybe go from positive definite to negative. But okay, you got it? So this is what Avik's talking about is really a non-trivial point, because if you want to here it is. You see, here's 0 maybe, and maybe here's this cone here. I'm not drawing very well. All right. Here's the positive cone, and if you want to have a positive definite bilinear form, this thing has to stay in the positive cone everywhere. So it's a non-trivial condition. Okay? A Riemannian metric is a section of the bundle of bilinear forms that is positive definite in the sense that at every point it's in the positive cone. In the sense you pointed out, its eigenvalues are positive. Okay? In the sense that length is positive. In the sense that what we were just talking about, after basis change, it's more or less Euclidean geometry, except you have these different lengths, which are the eigenvectors. Okay? That's what is a Riemannian metric. Okay? Good. Riemann understood the importance of that. And what Riemann understood I think, is associated to a Riemannian metric in a canonical way is a connection. Okay. Let me say it again. Amin gives me a connection. You give. Is it right, Amin? Am I saying your name?
Amen.
Iman. I converted a Russian friend of mine's name Amin, and I translated Iman. Sorry. Iman. So, Riemann, you have a Riemannian metric. It's a positive, definite section of the bundle of differential forms, of bilinear forms. Definition. And associated to this is what we call a metric connection. Yes.
Why is it called a metric?
Why is this called a metric?
Why does it give
Because I don't know why. Because it measures, for one thing, it measures tangent vectors or measures vectors in a bundle. I think that's a reasonable thing. It's measuring length and angles. So it's a metric in that sense. The confusing part is what I started with here, that people call this distance function a metric. And I started with that because I wanted to tell you, forget it. Okay, a metric on a Riemannian, on a differentiable manifold is what I just said. It's really a metric on a bundle on a differentiable manifold. The metric on the manifold is on the tangent bundle. Okay. And there's something associated with this in a canonical way. And this thing is what is called torsion-free. Whatever that means, that you, in order to make it canonical, you need for this thing to be torsion-free. And guess what? I'm in the manifold. And I'm over here, say at x 0, and I have another point on the manifold x1, and I connect these points with a curve. And everything I just said there has nothing to do with Riemannian geometry, does it? I mean, it's just a point on a manifold and stuff like that, right? Okay. Let's take nabla to be the metric connection, whatever that is. I told you, if you have a curve and a connection, you know how to start here with a vector here, y, and push it, parallel. And you end up with a vector here, parallel translate from x0 to x1 of y. Isn't it true? I told you if you have a connection, there's a canonical way to transport vectors along curves. Okay? Take a vector here at the beginning with respect to the metric connection. You have a metric here. Riemann called this bilinear things G. So we have the metric here on this tangent space Gx0. Right? I have the geometry of that tangent space. And I have the geometry of this tangent space, Gx1. Now I have something. I have a connection that tells me how to take a vector here, move it along this curve, and get a vector there. Well, if I take another take a z here, I'll move it along, parallel transport, use this connection. I get a parallel transport from x0 to x1 along the curve. We should write here gamma, because gamma defines this thing, of z. Now what is the dream here? What is the dream here? I parallel translate by something that's canonically related to the metric. I parallel translate by something that's canonically related to the metric. I take a curve that goes from here outside and goes out into the toilet. Yes?
So you want it not to depend on the curve?
Huh?
So you want it not to depend on the curve?
It'll depend on the curve. Unfortunately, it depends on the curve. That's it, yeah?
But then you want to maintain that the bilinear forms give you sort of similar things.
Bravo! I don't have any money, but bravo! Did you hear what Abik said? He said, look, this thing, this connection is defined by the metric. I just told you that, I haven't proved anything. Yeah. You use the connection to go to the toilet, And there you can, some curve to the toilet. Unfortunately, or fortunately or not, it depends on the curve, right? We could go over and have a sandwich and come back and then go to the toilet. Okay? You go to the toilet, right, by this connection. And there's another curve that does that, so let's keep a fixed curve, not the one to go to have a sandwich, just a fixed curve. You parallel translate using this canonical thing. You take another thing, parallel translate, you get another vector and so on. What has to be? Is what Abig says, that has to be an isometry. What does it mean, isometry? It means the map, let me write it down. You take these two vectors here, push them over here. The metric applied to the two vectors here is the same thing as the metric applied to the two vectors over here. Right? Right? That's the word isometry. G x1 of parallel transport from x0 to x1 along gamma of y, p parallel transport x1 along gamma of y of z. That's over here at x1 equals g x0 of y z. Now you can see why this subject looks technical. If you would start writing this down in a basis, what that would look like. And that's the reason these horrible Christoffel symbols and this horrible stuff that people make you do, they beat you on the head, they take physicists and make you, bam, 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 it's terrible, right? You don't know what the hell you're doing. You're just making these calculations. Einstein told you you ought to do that. Isn't that true? It really is terrible. What you are doing is saying, if you take the metric connection, which is canonically associated to the Riemannian metric given to you by whoever, by Riemann. It's not, the metric's not canonical either, by the way. I mean, you have all possible positive definite sections. There are many, many metrics. Yes? There are many, many metrics. But if you take one of them, it's canonically, and then take the canonically related connection, and I claim Riemann had that in mind. Yeah? Then parallel transport takes vectors over there, and this is a statement, is that parallel transport is an isometry. Okay. So I've gone to about the limiting time. I just want to say the words again that you need to keep in mind. Manifold, tangent vector, vector field. All of that's just manifold stuff. Put these in a bundle. Tangent bundle, that's key. General vector bundles will be important. Why not just talk about vector bundles in general? Okay. Connection. Connection gives you a way of differentiating sections of a vector bundle with respect to a vector field. We will formalize exactly what that is. Notation-wise, that's nabla x, where x is a vector field. That's the thing that differentiates the set. That is a connection. Connection defines parallel transport. It means that if you start at a curve, with a curve, it means start with a vector at the first point of the curve, and you move it parallel along this curve with respect to the tangent vector of the curve. It means that this doesn't change. So it means that a certain nabla, well, it means nabla of the derivative field with respect to this thing doesn't change. This is the right definition of parallel transport. Okay. This transports the vector along the curve parallel with respect to the connection. Okay. The space of all connections is a huge space. We talked about it. You got partition of unity is some huge space. I will talk about this a little bit about physics. The so-called gauge group acts on this space. And actually, it is of interest to look at this space modulo gauge transformation. Physicists also talk about fixing a gauge. So there are all sorts of words here that are going around. It doesn't matter. You have a huge space of connections, and you're looking for good ones. Riemann found a way of good ones. He said, what I like to talk about is a very natural notion of geometry given by bilinear form. He calls these bilinear forms G. Guess why? Gauss. That was his teacher. Oh, Professor Gauss, I'll name a bilinear form after you. Yes, that's Germany, you see. Professor Gauss. My students never learned that. I have a horrible name, Huckleberry, nobody would call it. Gauss has a great name, you know, Gauss. So G for Gauss, at each point it is a bilinear form. It is positive definite for Riemann. For Einstein, in elementary relativity, is not positive definite. It has one negative eigenvalue, right? So for Riemann, it's positive definite. And there is a canonical connection associated to that. It's called the metric connection. And the wonderful thing is, parallel transport by the metric connection is an isometry. Yeah. Okay? Now, I will repeat this lecture tomorrow, but with detail. Okay? Thank you.